All right. Hello, everyone. Welcome. Thank you very much for joining us today. I know it's maybe very early for some of you. It's getting kind of late for some others. Thank you very much for being here. So today it's my great pleasure to introduce you to this wonderful talk that you'll see by Professor Melvyn Sim, who is a Provost Chair Professor in the Department of Analytics and Operations at the NUS Business School in Singapore. And his research, I'm sure everyone is very familiar. That's why you are here. But just to say one word, optimization under uncertainty, of course, with various applications. And currently, he serves as a department editor for AMSOM. In the past, he has also helped with many other important journals. So today, he will tell us a little bit about this recent work on robust decision models with estimation and prediction. Thank you very much for joining us, Melvyn.
No, thank you, Merv. Thanks a lot for organizing this webinar. I think webinar becomes very popular during the COVID, and now it seems to be the norm. It's great because it really reduces travel costs, and people can share ideas at a much sustainable way. And thank you again for inviting me to this stochastic programming webinar series. Right, I'm going to talk about work that is still in progress, and I thought there's something interesting that I can share, right, from a different perspective, right. And just to acknowledge my co-authors, the first author, Ziyuan Luo Ziyuan, like to call him. He's in Technological University of Munich. He's still a student. His advisor is Jinghui Xian, is also one of the co-authors here. And this is also a joint work with my former students, Chen Zhi, or Zhi Chen, who is now assistant professor in Chinese University of Hong Kong, and also my colleague and also longtime collaborator with me on the robust optimization software, right? Uh, I'm going to start with this on the challenges of optimizing decision under uncertainty. This is the agenda of my talk. Feel free to ask to stop by if you want any clarification, right? And I'm okay to I've not presented this, so I'm not sure how long it will take. So, but along the way, if there are some pressing questions or you violently disagree with me, uh, and like me to clarify certain things, please do so. I will appreciate that, right? Right. The challenges of optimization under uncertainty. I think I can summarize why this optimization decision under uncertainty is challenging by quoting George Box, who's a statistician, that all models are wrong. The models here refers to models or uncertainty, right? If you want to look at uncertainty, it's not necessarily easy to describe the future uncertainty exactly. So this to me is a very important things that we should be mindful of, right? I will illustrate example of why models are wrong and propose another model which could potentially be wrong, but there are certain nice aspects that we might want to consider, right? So when when I studied operation research about 20 years, more than 20 years ago, we take a lot of classes on OR, right? We learn about stochastic process, decision making under uncertainty, dynamic programming, stochastic optimizations, linear programming, and many of these tools. But let's review what are the expertise, right, that we might require to solve a problem regarding decisions under uncertainty. When I talk about decisions, it involves human agents that would favor a particular decision over another. I'm not talking about optimization like machine learning where I need to minimize the loss function, right? That has no impact on whether that decisions will how the impact on how the decisions will affect a human agent, right? So one uh one expertise that we require is possibly the applied probabilities, right? The idea is that you will model the decision problem as a stochastic process, stochastic as a way to model uncertainty. And for those, we know that this expert will focus on formulating a stochastic process that has analytical tractability, so that I can say something about the descriptive statistics of the optimization of the uncertainty in future, right? Uh, we might also require a decision theories, right? In the following sense, when you want to optimize, improve decision making, you must be able to rank various decisions. In other words, whether I prefer solution A over B. Optimization, in this case, you want to optimize over potential infinite number of possible decisions, right? At least the first thing you need to do is to establish a decision criteria. Decision theories will come in to help us focus on the right decision, right? I mean, right decision defined by decision theories is that the usual focus on rational agents, right, with potential extensive computational power, right? And that seems to be a benchmark on how decisions should be ranked, right? These are the gold standard as we taught in OR or operation research class. And of course, we need a statistician, right? That's how we link data to the stochastic process. We need to estimate parameters of stochastic process from data. And for statistician, they are mindful about the convergence, right? How fast, right? How well we converge our asymptotic results as data increases, right? Assuming that the data can be collected as independent samples, how fast you will converge, right? As data increases, right? And of course, we have the optimization expert, right? We are obsessed with obtaining the best solution for a decision problem. And the focus in this case will be how fast the convergence is and whether solution can reach optimality, right? Optimality, right? So these are the various aspects, right? To some extent, as I mentioned, right, all models are wrong, right? We have different people, different expertise trying to address the elephant in the room, but we can only view certain aspect. And this is a parable, a parable in the East that many of us are familiar with, the blind man and the elephant, right? I won't dwell too much on this, but I think everyone knows the story, right? I'll try to relate this parable to this example, right? Let's look at a portfolio management problems where you want to invest in N stocks, right? There's uncertainty in the future stock returns because what you want is to maximize your return, right? When you invest, right? But that return is uncertain. It can only occur in the future. Individual stocks here has a stochastic, is a random variable, right? In other words, they might come with a distribution, right? That you do not know at the time when you want to when at the time when you receive payment, right? At the end of the investment, right? And your decision variable is X, which is the vector in Rn, and the future returns is a transpose of the stock's returns vector and the portfolio allocation vector. So this is something that we can characterize. This is something that, in a nutshell, what the portfolio optimization problem is about. What the applied probabilist will do will be to model the random variable as something that's analytical tractable. The portfolio return, if it's arbitrary random variable, it'll be difficult to evaluate the portfolio, right? But when the return is normally distributed, right, with mu being the mean, sigma being the covariance, right? You can the portfolio return, right, which is R transpose X, right? It's a normal, the composite random variable is a univariate random variable with mean mu prime X and variance X transpose sigma S, which is analytical tractable. You do not necessarily get the same description if X, if R is uniformly distributed or other types of distribution, right? So I think the natural choice for this problem is normal distribution, right? Multivariate normal distribution. Addition theories will assume that the agents are rational, right? And the classical rational axioms will assume that agents would must follow this expected utility. It's a very nice way of arguing why people should use exponential utilities based on a set of axioms complete ordering, which means I can always rank a decision whether A is equals to B, A is better than B is better than A, or there are indifference between the two. There's so transitivity, right? If A is preferred over B is preferred over C, then A is preferred over C, and so forth. The independence is something that's very interesting, right? It assumes that suppose there are two returns, right? That your indifference, portfolio A and portfolio B, right? This random return, right? And suppose you do a composite random variable, right? And with probability P, you get A, probability 1 minus P, you get C, over another composite random variable where you toss a bias coin. With probability P, we get B, and probability 1 minus P, you get C. Because the common routes, there are common terms, you can just remove it, right? And this composite random variable should be indifference because A is indifferent to B, right? So if you believe the rational agent should be consistent in this choice, then the only way to rank them is using expected utility, right? And there are many types of utility to use, right? And one of the utilities that is consistent with risk aversion is to consider this exponential utility, right? And remember that exponential utility, expected exponential utility is related to moment generating function. And you know the moment generating function of normal distribution can be expressed in closed term. And very nicely, we assume exponential utility, you can actually calculate the certainty equivalent of the portfolio return in closed form as a quadratic uh, function of x, right? So in this case, the utility is something that you want to maximize, okay? And we are not done yet. Where the statistician comes in is we want to estimate the distribution, right? And turns out that estimating normal distribution is easy, right? If you look at the criteria of maximizing likelihood. If you maximize the likelihood, right, based on the data, you can actually express the mean and covariance, the estimate of the mean and covariance that maximize the likelihood to be the empirical mean and the empirical covariance, right? And nice, right? And if you put everything together, right, and you ask the optimization expert, right, you suggest to maximize this concave quadratic function, right, subject to the portfolio allocation decision. In this case, the sum of all the weights is equals to 1, right? It can be negative if you allow short selling, right? And an example is that how could this one way, in this case, for example, you need to specify K, the risk, which is relates to risk tolerance parameter. Additional theory is tell how you specify K, right? Another way is to anchor this to be equals to tau. I want a portfolio with a certain return. So you fix the expected return, which makes sense. I want a long-term return of tau, right? And this can be formulated as the celebrated Markowitz portfolio optimization, where you minimize the variance of portfolio subject to return to be equals to tau. Okay? What I'm going to do right now to show how this might go wrong is, suppose I want a portfolio that is the same as an equal weighted portfolio. Equal weighted portfolio. So I set tau equals to 1 over n, and the returns of the equal weighted portfolio, right? So in this case, 1 over n means the amount of investment I put into an equal weighted portfolio for each stock, right? So if the total is 1, so each of the stock I invest is 1 over n dollars, right? So this is the expected return of an equal weighted portfolio. And what I want to do is to look at the following, right? In a realistic setting, right, I estimate the mean and covariance for data, right? This data are collected over time. In other words, I don't have a million of data, and they may not be stationary, okay? And I want to evaluate what I solved the Markowitz model, right? I solved this Markowitz model, right? And with the mean and the covariance estimated from data, right? And I compare with the performance for equal-weighted portfolio. In this case, in this experiment setting, I try different, on the x-axis is the different amount of data I use in the in-sample training, right? Ranging from 600 to 400, right? One thing for sure, you realize that the mean return is not necessarily the same as the equal-weighted portfolio. At certain level, right, the more the data I have, it seems that the worse out of sample mean return I have. And remember, the Markowitz model tries to minimize the variance. But you see that the equal-weighted portfolio has the lowest variance. The optimized portfolio in which variance is supposed to minimize has a higher variance, which is to some extent not what you want. Optimization should get the solution better, right? But it doesn't. The reason is that the optimization solve the in-sample problem. And since all models are wrong, we do not necessarily believe that the outsample will be better as well, right? Outsample could be worse, right? Which is reflected in this case, right? This is not a cherry pick example. There are studies to show that, empirical studies show that one over n portfolio strategy is pretty good. In fact, it outperform most of all the portfolio allocations strategy out there, right? Now, for that matter, I know I'm preaching to stochastic optimization expertise already. I just want to mention that these are the problems that might arise in practice, and I want to look at let's look at some other ways to address this model, right? I'm going to focus on mention something about decision models. I do not want to call it optimization because optimization, the application of optimization is too vast. It can be machine learning, forecasting, statistics, but I want to look at decision models where it will impact human decisions, human agent, right? Uh, so let's look at in the simplest case, a deterministic model. I'm going to focus a simple case where the objective function is going to be linear, right? And there's one attribute function, right? That's for simplicity. And the goal of this is to determine X. X is the here and now solution. Here and now solution, solution that I can implement now. That's what matters most, right? And Z hat represent the specified input vector to the model, right? The specified input vector to the model, right? In the deterministic model, this just estimated value or some values that the decision maker, right, the model put in, right? And the attribute function here can be expressed as an optimization problem, right? So it can be expressed as an optimization problem, linear optimization because of its applicability, right? And in this case, you look at that for the stochastic optimization problem models, this is a recourse problem where Y is a decision, in fact, it's a fixed recourse because B is a constant. It's a fixed recourse problem, right? And the decision Y is a weight and C or recourse decision that is taken after evaluating Z as well as X, right? So there's a distinction between X and Y. What X is it's not a function of Z, but Y is a function of Z, right? So this is one attribute function, right? There could be multiple attribute function. Example, if you work on vehicle routing problem, FM, in this case, the multiple attribute could be the arrival time of a vehicle at a particular customer node, right? And TM will be the deadline that is required to arrive at that customer node, right? There could be multiple customers, so there are multiple attributes, okay, in that regard. In this case, in the deterministic case, right, if Z hat is deterministic, then I can express this as a large optimization models involving the recourse problem, right? Uh, in the single optimization, deterministic optimization framework. Now, I'm going to introduce uncertainty, right? The simplest way of introducing uncertainty, I'm not is to assume that uncertainty comes from a set, right? And I'm going to call this the budgeted robust optimization, which is actually the classical robust optimization. The simplest model of robust optimization is is first to define a uncertainty set that is a subset of the support set that contains the specified input, right? The specified input will be z hat, and there's uncertainty to the outcome, the actual outcome from this specified vector. This specified value could be estimated value, and outcome could be different from this specified value, right? And this uncertainty set is defined by a disparity matrix, which is a delta over here that measures the distance between z, which is the future value parameters that you do not know, and the specified z hat value, right? So could be a norm, right? And the parameter gamma over here is the budget parameter, disparity budget parameter. So as gamma increase, you allow the uncertainty to vary much larger from much to very uh, within a support set, right? But proximal to z hat. The proximity is controlled by gamma, right? So this is what I call the budgeted robust optimization. But it's not necessarily easy to solve because this function could be a second stage problem, and which is technically an intractable problem if you want to solve this exactly, right? Oh, but let me just focus on the disparity matrix, which I'll look at it, right? A disparity matrix is usually could be expressed as a norm, right? So that it's usually expressed as a norm, and then there are many ways to describe a norm, right? Let's just focus on LP norm here, and reflect the distance, right? There's a norm over the norm. There's a difference between z and the specified input, and you can also normalize it by a deviation matrix, right? So deviation matrix will be useful if you are looking at data that has different set of dimension that reflects about different units, and having this deviation matrix would put everything together in the same matrix so that you can be the distance, it make more sense, right, from that perspective, right? So the choice of the norm can impact the tractability, right? When p equals to 1, use one norm, right? And in certain cases, that can be expressed as a linear optimization model, right? The robust constraint can be expressed as a linear optimization model, right? And that turns out to be the key idea in my first paper, The Price of Robustness, which turns out to be very highly cited, using simple ideas, one norm, right? And it turns out to be highly tractable, and because of its tractability, there's a lot of more use case for that model, right? It isn't very sophisticated, but it nonetheless is quite popular. So the budget, again, this is a budgeted uncertainty, right? I did mention that exact could be difficult to solve, and there are tractable approximation available, right? And I'd like to, for those who are familiar with robust optimization, right, to build tractable approximation it can be very cumbersome because it involves duality and putting those dual variables, and depends on the uncertainty set. Building this can be very complicated. And for those who work on robust optimization, I would like to at least introduce this software, which I work together with my co-authors, Zichen, for example, Zichen and Xiongpeng. Actually, most of the code is written by Xiongpeng, my colleague Xiongpeng. And we have this software, stochastic optimization made easy, right? It's based on the papers you have written. And what we want to do is facilitate the modeling of robust optimization model. Over the years, I find that there are not all models, not all robust optimization works well. So it's important to, in my opinion, to have a quick way to test whether various models works, right? Not from theoretical perspective, but evaluating on real data, right? And I find having a software like Awesome to be very, very effective in terms of finding out what are the models that works and on different kinds of problems. So I think it is also a very good, I use this in the undergraduate teaching because it's easier. You can use it for simple linear optimization, right? You can change the different solver. It supports Gurubi, Mosaic, right? Cplex, and also more recently C-opt, right? It supports semi-definite programming as well, second order constraint, exponential cone, right? And I'll show you that using this is quite, you can streamline the formulation so they can focus more on the how well this your models perform. Right. So one thing that always comes up when I work on robust optimization is how do you specify the budget parameter, right? The earliest proposal, they look at very simple models, uncertainty model, right? With some assumption of random variables. And they say how they will look at how the solution of the robust model will perform in the chance constraint. So they provide some probability of statistical guarantee. The other thing is to look at whether this model can be, how easy to interpret this model. The interpretability will be very much the same as much inspired by my first paper, The Price of Robustness, where the parameter is what we call the budget uncertainty. And the budget uncertainty, gamma refers to the number of uncertain parameters that would deviate in extreme cases. So you by controlling this number of extreme cases that you are willing to accept as a form of robust characterization, we can, there's a way for decision maker to specify gamma, right? Another way is to look at statistical guarantee, but only problem is very difficult to know that we don't really know distribution is and the other thing is that it's still based on a assumed model that we will not know how well it actually performs in practice, right? So the weak relation to chance constraint is that you can easily infer that if X is feasible in this robust constraint, assuming that you can solve it either exactly or approximately, you know that it's going to be the probability of the constraint to be violated is less than the probability of this this random variable evaluated on disparity matrix to exceed gamma, right? So the greater the gamma, right, the higher chance that the higher performance on the chance, and higher probability that this constraint is going to be valid. Of course, this is a naive bound, right? But it works for all functions. For functions that has properties, you can actually come up with better or even close some solution, right? But for generic function, this is the best that you could do, right? And more importantly, I do not know the probability bound. If you do not know, you do not know how to evaluate this probability, you don't really know how to specify gamma, right? So in optimization under uncertainty, I strongly advocate a satisficing decision model. In other words, instead of maximizing, right, an objective function, my objective function is C prime X, I am advocating a satisficing approach. In other words, I don't use the objective function as to minimize cost, but bring that to the constraint, right? Okay, a satisficing model here is inspired by Herb Simon, who coined the term satisfy, which is a combination of two words, satisfy and suffice. And it's very much driven by human bounded rationality of humans. They do not human behavior to achieve a least minimum level or target, but not necessarily to optimize the value. So instead of talking about optimization, I'm talking at satisficing, putting the objective C prime X as a constraint state. Okay, there are also empirical findings that managers are primarily concerned with target returns, right? If you ask them to articulate risk and so forth, right? So target becomes, in my opinion, is a way to articulate risk, right? Especially in uncertain world, right? The first satisficing model is the same time where chance constraint is introduced by Chance and Cooper, is a very early model that look at the maximizing uh, of this constraint, right? Maximize the probability that constraint be feasible. In this case, I remember the previous model I have is to minimize cost, but I now relegate this cost to a constraint and specify V naught, V1, right? Specify V1, right? So in other words, I'm not minimizing the cost, but I'm okay with the cost falling below V1, right? And maximizing the chance constraint, right? It turns out that this is not a popular model. We heard of chance constraint, but rarely we'll hear about the P model. But in my opinion, I feel that I'm a strong opinion that in optimization model, we should be optimizing P model, right? Maximize the probability of achieving target. It makes sense in a lot of settings, right? Under uncertainty, right? I will look at, of course, there are questions on how to evaluate P, right? And so forth. But let's try to bring this P model to the robust paradigm where distribution is not, where do not have distribution, right? So it turns out that I was interested in robust optimization, no, robust satisficing decision models for a long time. In fact, after I graduated, from my terminal degree in 2004, I started to work on satisficing model. I fortunate to work with David Brown from Duke, and we came up with something called what's the underlying properties of satisficing measure, which is analog to coherent risk measure, convex risk measure, and we bring that to the satisficing paradigm. And it turns out we can also extend it, the idea of prospect theory, but from a perspective of satisficing model. And that's our second paper also in management science, right? And using that as a paradigm, there are ways for me to look at decision model from satisficing. And more recently, I work on data-driven perspective, and a paper in robust satisficing that recently appeared in Operation Research, and also include how I could have site information or context-specific information in this data-driven robust satisficing framework, right? I'm not going to cover those data-driven settings. A lot more complex. I'm just looking at a pure robust optimization model. And an analog of it is to look at this budgeted robust satisficing, right? And the budgeted robust satisficing here now has gamma. Instead of fixing gamma, and maximize gamma, right? Same thing, the objective function is now relegated to the constraint. And I choose V1 to be greater than V. Remember, V is the objective function of the deterministic optimization model. So robust satisficing, I allow objectives to be higher than the lowest possible objective value that from a deterministic model. So in other words, the difference V1 minus V2, right? This is the additional cost, right? Or additional price you're willing to pay, right? To ensure robustness, right? And robustness here in this case is the size of uncertainty set. The larger the size, right, the more robust the solution is to uncertainty. So the difference here, in fact, it's more natural to call V1 minus V the price of robustness, right? Something that's easier to specify than the size of uncertainty set, right? So, the budget uncertainty here, so this is a robust, satisficing model, right? And the budgeted robust satisficing model can be expressed as a quasi-concave maximization problem where you can do a binary search on gamma, right, to find the most robust, the largest uncertainty set to solve this robust satisficing model. The difference with the robust optimization model is how you specify uncertainty, how you specify your preference, right? The preference for robust optimization is to specify gamma, which is not easy to specify, right? Which is more abstract. The way to specify a robust satisficing model is to specify V1, which is related to cost, right? At least it's in the same unit, right? As the deterministic optimization. So to some extent, specify V1 is much easier, much more interpretable compared to gamma, right? Now, I would like to bring in another type of robust optimization model, which is commonly known as the globalized robust optimization, or sometimes the comprehensive. But earlier it was known as I can't remember. Is it global or generalized or yeah? But it was later changed to globalized. But I would prefer to call it the tolerated robust optimization model, right? For following reason, right? So in this tolerated robust optimization model, uncertainty is allowed to vary within the support, right? In the budgeted, right, uncertainty is control. You kind of control uncertainty to be within this uncertainty set. But in a tolerated robust optimization model, right, allow uncertainty to vary within the whole support. But I allow the constraint to be violated. The violation of constraint is limited by this kappa multiplied by the same disparity matrix. There's no more disparity matrix in uncertainty set, but this disparity metric is now uh, moved up to the constraint, right? And this kappa can be related to the tolerance parameter, disparity tolerance. If the disparity tolerance is zero, means I do not tolerate any violation, right? You would what you get is f prime x z smaller than tau for every z in z. So this will be insanely robust. No matter what happened, this constraint will be satisfied if kappa equals zero. So if you specify kappa, right? If you know how to specify kappa, you will know how to specify this tolerance parameter, right? Whenever it violates, whenever very interesting, if z is not the same as z hat, the specified value, this constraint can be violated, but the level of violation is controlled by this. So in other words, a tolerated robust optimization model, it tolerates the magnitude of violation that's proportional to the distance of the specified input, right? A smaller violation from z hat means you get a potential low violation of the constraint. But if the estimation from z hat is so large, right, you would expect a larger violation, but there's nothing much you can do about it. So you can do a profile chance constraint, which is to some extent related to stochastic dominance, right? Where you can specify the probability that the violation of the constraint by kappa r, right? Kappa r is smaller than the probability of this disparity matrix when evaluating the random variable tilde z, right? The disparity of random variable, right? From the distance from the specified input to be greater than r. So again, and this is true for all r greater than zero. So it's not just evaluating the probability of violating target, but also we look at profile of how likely it's going to be, how the constraint is going to be violated by different levels of violation, right? Kappa r. Kappa equals zero. If at the value of zero, notice that if r equals zero, you get the probability of violation to be smaller than 1, which is not really what we may not be as great as the budgeted robust optimization, because the budgeted robust optimization allows you to specify the probability of violating tau. But this one doesn't necessarily avoid violation of tau, right? but control level of violation above tau. Okay, so so there's some benefit of this targeted robust optimization, but and at the same time, we can do a satisficing model, which in this case, the targeted robust satisficing model, right? Here in the targeted robust satisficing model, kappa is not a parameter you specify, but it's a parameter you minimize, right? The nice thing about this targeted robust satisficing model, which I like a lot, is the tractability. Because now the decision variable is x and z, they are all convex, right? If this function is convex in x, this is a convex optimization problem, or potential infinite number of constraints, right? But nonetheless, this is a convex optimization model. Oh, again, how we specify V1 is also similar before, right? I choose V1 to be greater, a value that is greater than the solution to the deterministic, the objective, the lowest possible solution of the objective of deterministic optimization model. So I provide some leeway. I don't require to have the lowest cost, because the lowest cost is not meaningful if the constraint gets violated, right? So in this case, I want to have the 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 lowest solution that's least fragile by minimizing the tolerance that the constraint will be associated with the attribute in terms of violating the target tau. Okay, so I can put everything together. I can combine the idea from the targeted robust and budgeted robust. And now in this case, there'll be a dual parameter kappa and tau, and you can get similar probabilistic profile guarantee as follows. But in this case, you can also translate to a satisficing framework, but now with two targets. In the first target, I maximize the size of the uncertainty set. And the second target, I minimize the tolerance parameter associated with this. I won't delve into this. But the main thing about this thing, I can look at the various form of robust optimization model and say that these robust optimization models, right, is characterized by this metric, right? The main focus of this, what kind of matrix do you choose, right? And for that purpose, I have only 15, about 20 minutes to look at this matrix. But I think it's important to go through those basic. I don't think I have time to cover everything, but just want to motivate what I'm doing, right? Now, I have provided a background and say that the disparity matrix is is the most important aspect in characterizing all the different types of robust models, right? It can be a targeted, budgeted. And disparity matrix can be expressed in this case by these two parameters, the specified input, as well as this D, right? In this case, the disparity matrix, right? The normalization matrix, right? And suppose we have data, right? How would we estimate this D from data, right? D as well as Z hat from data. So that's the goal, right? And I would try to look at it from the probabilistic perspective, probabilistic guarantee of the robust optimization. I want to motivate this from the robust optimization framework. The reason is the following: because I'm using this disparity matrix to characterize robust optimization model, the estimation should be related to that, right? It's very different from so there's some form of synergy in terms of how I want to do the estimation model. It's not necessarily minimizing an arbitrary loss function, but it's related to how I want to construct the robust optimization model. A way to look at this is to observe that suppose I have a penalty function over this deviation metric, right? Uh, and suppose I know the distribution, right? And I choose D, right, I fix P, I choose D and Z hat in a way that this constraint expected value is smaller than 1, right? You can show that my Markov inequality, the probability of this objective exceeding tau plus kappa R is smaller than 1 over the reciprocal of this deviation penalty function for R greater than 0, right? So this could be a design parameter. Suppose I want a certain profile of violation, right? Then I would know how to choose D and Z hat, right? That satisfy this profile chance constraint. Okay, so in other words, suppose I specify the penalty function and ensure that this constraint is always true, right? Then you have a nice results on how the profile chance constraint is going to look like, right? At least this is always guaranteed for any distribution that satisfy this, right? And I don't really need to know what kind of distribution is this, right? Suppose I can choose this penalty function to be R to the power of 7, right? I would this constraint will be you ensure that using the same probability distribution, the probability that the constraint will be violated by kappa R is smaller than R to the power of -7 for all R greater than 0, right? And you can choose different types of function to in order to, it can be exponential function so that the probability of violating will decrease exponentially. Okay, now what's the objective function that I would like to choose to minimize or optimize, right? In the context of robust optimization, the conservativeness of the robust optimization model depends on the size of uncertainty set. And turns out that you can actually look at this norm, right? And this could define a confidence ball, right? The volume of this confidence ball or confidence set is related to the determinant of D, right? Of the deviation matrix, right? And this related to that, right? So the volume of the norm ball is related to the size of the uncertainty set. The larger the size of the uncertainty set, the more the conservative the solution, robust solution might be. So if you want to minimize conservativeness, it might make sense for you to find the smallest uncertainty set that would satisfy the probabilistic bound, right? So a way to look at that is in the tractable optimization model is to minimize the determinant of D subject to this constraint, right? And Z hat and D becomes the decision model. It becomes the parameters of this estimation model, right? And this is very much motivated by robust optimization model. So you have the volume of uncertainty set, and this constraint ensure the probabilistic guarantee, right? And the idea is that suppose I have historical data, and what I do is to plug in this P over here, right, which is the empirical distribution, right? And so this is something that we know how to compute, right? And we put in this D to be greater than this diagonal R, right? So this is to ensure that the volume of this uncertainty set doesn't goes to 0. It goes down to 0. It's not a well-specified problem, right? And in machine learning or in regression, right, this could so this could happen where the whole the yeah where the regression parameters can lie on a plane, right? And in other words, the volume uncertainty set is 0. So very similar to regularization, this regularization is just to prevent that the volume doesn't go to 0, right? The volume uncertainty set doesn't go to 0. So this, what I call this, the minimum volume confidence set estimation problem can be expressed. It's not a convex optimization, but it can easily be converted to a convex optimization model, right? The objective here is to maximize the root determinant. It can also be the log determinant, right? And it can be supported by a solver that a coding optimization that has that supports semi-definite programming, which includes in this case the copt and mosaic, right? Uh, um, just for example, suppose I restrict to L P1 norm and the power function, the penalty function is restricted to power function. Estimated problem can be expressed as follows, right? With different choice of P1 and P2, right? The estimation problem here in this case can be implemented in Mosaic, sorry, in Asym using this few lines of code, right? Just to show you what happened, right? Suppose I change P1, right? I change P1, I can change the shape uncertainty set, right? If I change P2, right, I change the penalty, right? And realize that when I choose different level of P2, right, when P1 is equal to 1 estimation, this is less sensitive to outlier. If I increase P2, right, this is more sensitive to outlier. So an estimation that you have a leeway to adjust P1 and P2, right? P1 could impact the tractability of the model, right? But P2 could adjust the sensitivity of your estimation to outliers, right? So yeah, of course, which one works well, I do not know. I think we should try experimentally, right? And see on what set of data it works well, right? It's just like machine learning. Machine learning is becomes successful because there's a lot of data set to test out what kind of problems works in different set of data. I hope we can do that for optimization as well, for audition problems as well. One thing it's interesting to know that sometimes for if P1 and P2 equals 2, we can actually obtain closed form solution, right? The estimate Z hat in this case will be empirical mean and D star will be a square root of the covariance matrix, estimated covariance matrix. Okay. Now, the next one, I just want to say that I can extend this to beyond regular symmetric shape. I can extend it to an asymmetric confidence set. Over here, it can be done. You see that shape, this is not a regular shape. This shape is asymmetric and it could better capture the uncertainty, the distribution here, compared to a regular symmetrical shape, right? The estimation model looks like this. You can calculate the volume, right? The reason why it's expressed in that way is it allows us to formulate as a tractable optimization problem, right? And the shape can be calculated exactly as follows. And this is the optimization model that we solve. Unfortunately, this doesn't lead to a convex optimization problem, but we can use the alternative optimization strategy, right, by first fixing D and Z hat, then and in the second iteration, you optimize over the sigma underline and sigma overline and repeat the process. This seems to works well, right? And this is just to showcase that it can be done in the data-driven setting. It gives you a different kind of shape, right? In this case. And I like to extend it to a predictive model with site information, right? I think I would quickly go through this and I would stop there, right? Probably won't have time to go into numerical studies, but that's not important. That's not as important as in this talk. Uh, so let's look at in the data-driven setting with site information with covariate or their contextual information. There are similar terms, right? I call it site information. In other words, suppose the data comes in pair, there is a site information before the realized uncertainty ZW. So site information I'm going to denote by S omega. The realized value is Z omega, right? I'm going to assume a very simple affine prediction, right? Where the Z, right, estimated outcome is affinely dependent on the site information. I think this is good enough in the linear, so it's just like linear regression. To me, it really depends on creatively how you choose the site information. If I want to look at this can be extended to machine learning model where the site information will be outcome of a neural network, for example, or experts who are predicting the outcome, right? And that can be used in order to use a robust prediction model, robust optimization model. I can map it to this affine prediction map, but the site information will be the actual predicted outcome. So this could be a pretty generic optimization model. It could be an ensemble model as well, right? So and I can use the robust model by looking at the following. Suppose I have the predicted outside information, right? And use that to determine the value of X. Okay, to do so, right, I need I just give you an example. Like for example, in the unique commitment problem, the site information could be a weather information or AI expert prediction. Z could be the energy demand, which I want to predict from the weather information. X should be the production level of energy after observing this site information, right? In this case, this will be the predicted demand by after seeing the site information, and there'll be uncertainty from actual realization of Z from the predicted outcome, right? So the goal in this case is to estimate this too, right? Is to define this uncertainty set as well, right? My goal is to look at yeah, my goal is to so this Z, this delta Z yeah, my goal is to do the estimation problem here, which can be expressed as a same thing as is to estimate this Z not hat and this matrix Z hat as well as this T. This can be done from data exactly in the same way and by solving the convex optimization model. It can also be extended to asymmetric as well. I won't go in much into a detail. Right. And the nice thing is that we used P1, P2 is equals to 2, right? You obtain the ordinary least square problem, right? It turns out that I not seen how similar estimation models for other parameters of P1 and P2. And I don't really know what are the statistical properties. I know when this is 2 is related to blue, the best linear unbiased estimator, but I'm not sure how the statistical properties of this estimation look like. So for those who are statisticians who work in this area, these are something that I would like to know. And if you provide me some interesting insights of the statistical properties, this is something I'd like to learn as well. Right. And I think it's 9 o'clock, and I think I should stop here. I don't really have time to go into the numerical studies, and that's all. I'm sorry I couldn't complete everything. That's all. I'll now open for questions, nonetheless.
Thank you very much. Perfect timing. I will just stop the recording. So.